Okay. The homeworks for this particular topic was very simple, I hope. And I'm giving you a few just to get familiarize yourself with the concepts. So the first one was use a Venn diagram, because Venn diagrams are useful, so I want to have at least one exercise about them, to illustrate the set of all months of the year whose names do not contain the letter R in the set of all months. So what we need is a big Venn diagram that will contain all the months of the year, and then a subset of the months that do not contain the letter R. It's not contained, right? So let's start. January. Well, January goes here. So these are M, that's the months. Let's call it, okay, we normally give sets a single letter name. It's not necessary. In mathematics, you can do quite a lot. Let me perhaps also make it a little bit bigger, because there are quite a lot of months, right? Okay, so I'm going to call M the set of all months. So M is all months. And then R are the months without an R. Okay, okay, we just go January. So January would, of course, go here because there's an R in there, and same with February. March. April. Well, I hope we get a month without an R. Well, the next one is May. So we have May here. The next one also June, July, August, and then September. Well, that has an R in it, so it has to go outside again. September, October. Yeah, I have the habit of putting a little dot behind because I'm abbreviating, but I shouldn't do that because it looks like I'm making a new set here. So February here, September, October, November, and December. So somehow, by accident, perhaps a little bit, the months without an R are the summer months. And in Belgium, where I come from, people love mussels, French fries and mussels. If you ever go to Belgium, that's the thing to eat. Now, I don't like it, but most Belgians like it. And the saying is that the mussel season is the season where there is no R in the month. So this set R is also the set, the month when you can eat moule frites, as they say in French, or mussels and French fries in Belgium. Just so that you, if you ever get to go to that country. Okay. All right, so that's the first one, and you see, and what this illustrates is that we have R sitting inside M. And of course, that's by design, because R is a collection of months with a certain property. Okay. Then the other one that I want you to do was 17. That is a little bit, remember, we are doing proofs once in a while, and I want you to once in a while see a proof here. So what we said, what the question asked is, if A is in B, A is a subset of B, and B is a subset of C, show that A is a subset of C. Now, there are many ways of you can show that. Actually, one is pictorial, so a picture, pictorial. Now, that's normally not considered a true proof, but just to give at least convincing. It is convincing, but a formal proof I will give right away. But what does that mean? Well, let's make Venn diagrams. This is A. Now, the fact that A sits in B means that I can draw B around A, right? Later we will see, you saw this in the lecture. Sometimes you have A, and then you have another set B here that partly contains A, but partly doesn't. And that's how the picture would look like if you don't have really subsets. But here we have subsets. So let's get rid of this. And B sits in C, so that means, again, C can be drawn around B. And now, sits A in B, yeah, you can see it, but I am going to even show you better. There, A is in C. Okay? Now, that's pictorial, and that's not considered a formal proof. So what's the formal proof? Well, let's look at the definition that I gave in the text. What does it mean for A to be in the lecture, what does it mean for A to be in B? It means that if a little a lies in the set capital A, then little a lies in the set B. That's what this means. What does this mean? it says the same thing, but for B now and C. If a little b lies in capital B, then little b lies in capital C. Okay, I'm just now writing down what I know. So now is the proof. So here comes the proof. Start with A in A. Okay? I start with an A in A. I'll show you why I do that. So let's do that. Start with an A in A. Why am I doing that? Well, what do I need to show? Perhaps, okay. Let me explain why I'm doing this. What does this mean? Well, this is what I need to show. I'm going to write it here so that we don't get confused. So to show, because we don't know yet, basically the same statement. If you have an A in capital A, then that little a sits in capital C. I'm writing my C's this way so to make distinction with the symbol inclusion, okay? Subset. So if that's what we need to show. If we take in little a in A, then the little a is in C. Now a direct proof. How does a direct proof work? A direct proof of an implication, you assume the hypothesis. So, okay, so let me write it more correctly here. So assume A is in A. And what I need to show is that A is in C. Remember that? Okay. So A is in A. But I have an implication here. This implication, let's call that implication 1. So I'll copy it here. A in A, then A in B. I have an implication. I know the hypothesis. Modus ponens. You remember that guy? Modus ponens tells me I can make the conclusion. A lies in capital B. Now you say, okay, but I'm stuck because the other one talks about B. What? Now remember, let's go back. I'm doing this a bit formal so that you get used to what are these proofs. Very often we are much quicker in writing things down, but I want to be very formal. So this implication that I wrote down, A lies in capital A, implies A lies in capital B. That's a statement about little a. So it actually is not a proposition, it's a predicate, right? So remember what we said about this when we make statements in general, which are actually predicates, which is actually what therefore cannot be true or false because they're predicates. We really mean, what is really meant, so I do it in red here, is that there is a for all A here. Okay? So let's set up our proof more formally. I don't want to get distracted by the letters, and so I'm going to now write the whole thing more formally. I'm sorry that I keep going back and forth, but I want you to understand how this works formally. So I'm going to now, instead of with the original setups, I'm going to write down really what it formally means. Okay? So it says for all x, and since variables I like to call x, for all x, if x lies in A, then x lies in B. That's what this means, okay? Now, what does this mean? Well, if I'm going to universal quantify, I can use the same quantifier. Remember, I just erased this, but I'm now talking about this here, that for all x, if x is in B, then x is in C. Now, what do I have to show? I have to show that for all x in A, x lies in C. Okay, now I'm making it really formal by putting a quantifier in front of that. Now, we have said that if you have to show a universal quantification, you take a particular instance. This is universal instantation. You assume A in A is arbitrary. Okay? Okay, so before I can do modus ponens, therefore, I have to do something else. Do you remember what it is that I have to do? I have to do universal instantiation. Okay? So, for all x, this statement here, I don't want to erase this. This statement here, for all x in A, x is in B, I'm going to take a universal instantiation, which means I can replace x by whatever I want, and what I want is little a. So I'm going to do, let's go back into black, universal instantiation. I'm taking x equal to a. And therefore, the statement becomes, if A is in A, then A is in B. And now I can really do my modus ponens because I have A is in A. And so this universal instantiation, now I have modus ponens. I'm going to write it this side here. Okay, modus ponens tells me I can conclude A in B. I'm going to, what do I do now with the next one? I'm going to do another universal instantiation. I say, what do? Again, I'm going to take X to be A. And so the statement becomes, if A is in capital B, then A is in capital C. You see how we got around this problem that in the previous, I had a B there instead of an A. And the reason it looked that they were different elements is because we didn't universally quantify. But if we do everything really formal, then we see that what we're doing is very kosher. We just universal quantify, we take this universal instantiation in the second statement, not to the B that we originally had, but to the same A that I've been working with from the beginning. Okay? And so we think of this little A as a fixed element. It has a name, it's something that has a description, but we don't want to emphasize what it is. We just say there is this A, Mr. A, that lies in capital A. Okay, going on. So we have this statement as well, and we have another modus ponens, right? With modus ponens, I get A lies in C. So what is it that we needed to show is that for all X, X lies in C. But I have only this. Now, what we have shown that if A is in A, then A in C. And then we know that by what is called universal generalization, if you do this for an arbitrary A, then you can conclude that this is true for all A. So for all A's, for all X's, if X is in A, then X is in C. That's what we now formally proved, right? I'm saying we started from this assumption, we reached this conclusion, and we did this for arbitrary. That means for all X, if you start from X equals A, you can conclude X in C. And this is just what it means for A to be in C. So yeah, let me not write an equal sign here. That's a little bit misleading. So let me write it like this. That's exactly what it means. That is A in C. And that's how we say a formal proof of, remember then when we do formal proofs, we want to show off, right? And we say we make a little black box here and say, look guys, we did it. Okay. And so that's a very common way of proving things about sets. You really talk about universal statements, but very often you just take an instance and you work it out. So a much quicker proof would have just been, we start with an A in A, and we know that then A is in B, and so A in A and A in A, so we conclude A is in B, modus ponens. And then we have this statement, we had the B there, but we know that we can replace this B by anything we want by exactly universal instantiation. So A is in B together with A in B implies A in C. We now get A in C, and that's what we needed to show. This is how we normally would write down the proof, but if you really want to dissect it, that's what it is.